So, have you got those carry bags for the shopping?
Of course I have. So this one, tea. This one, not tea. Are they alright? They're good? Yeah?
I'm afraid not, to be honest.
No?
Apart from the fact that we don't buy anything but tea now, that's good. We'll get our elves to do the rest.
Yeah.
These things are terrible, absolutely terrible. If I put them over my head, I suffocate. The environment, it's gone. Polar bears, they're all dead, and penguins, forget about it. Look.
Oh, that's bad, that is.
She is not okay.
No, that's... Okay. So, carry bags...
No.
Out of the window.
Out the window, literally, out the window.
Yeah, gone.
You shouldn't see that coming. Yeah.
You can't carry the whole of our shopping with. There's far too much tea.
There is too much tea bags.
Yeah.
Thankfully, a clever guy, me, came up with something genius.
Oh, okay, an alternative, right?
Biodegradable bags. They're just like bags,
Yeah.
except they're biodegradable.
Oh, that's great.
Yeah.
What's biodegradable?
I don't know. Something about breaking them down or something, you know, hydrolysis, they break up. Simple
Oh,
stuff.
okay,
The
so-
scientist told me.
Alright, so if you drop them in like a pool full of turtles, if you
Yep.
the biodegradable, disappear, no turtle hurt.
No turtles hurt.
Okay, you use
Which is
bad
good.
bags, like the Powerman bags.
Turtles all die, extinct, gone forever.
Terrible.
Oh no, I love turtles.
Especially in soup.
Exactly.
So, plastic bags are made out of esters, right?
Yeah, polyesters and
Okay.
polyamides make up some of the stuff.
So you want to break them down?
We do indeed. So let's look at a polyester.
Alright.
In previous videos we've looked at forming them.
Okay.
This
So,
time,
say we'd formed one.
yep. I'm actually going to form the one we used in a previous video if you watched
Okay.
that. It's going to be the exact same one.
Oh. That is lovely, that is. So,
Thank you.
as always, the box goes over where the all repeat units and end lots of units. That's
So
so
it looks
we
like
have.
that. These are both hydrogens,
Yeah, and
all four of them.
that's
to-
not important.
Yeah, they're not.
So we formed it by removing water.
Condensation reaction.
So we're going to break it by putting in water.
Hydrolysis.
Yeah. And we're going to put it here. That's our ester linkage there.
It is, and you've got to notice that in an exam. It's not going to tell you where the ester linkage is. You need to be able to recognise it. But you can't. There isn't just adding water. There is actually two routes you could take to breaking this up. It's not
Two
just
pathways in life.
Yeah.
So we have our acid hydrolysis.
Water. Yep. And then there's the alkaline hydrolysis, or the basic hydrolysis.
Yeah, that one's well easy.
It's well easy.
So the acid one first.
Yeah, the acid one is simpler, really. We just use water.
Yeah, as water is amphoteric, it could do both, but we're going to use something different for the alkaline, just so
Yeah.
it's different.
So the water's being forced into there.
Yeah.
And you should know that when we're breaking up this carboxylic acid, it loves OH. It takes
It
the
does.
OH.
Because the alcohol's half always keeps the O.
Yes,
It's when they have a divorce, it's their CDs.
it is.
They
Yeah,
keep it.
they go to court. And of the H2O, we've taken an OH this way, so there's
Yeah.
an H left to go this way, which works out quite nicely in a second.
It is. So what we're going to do now is we'll take you through kind of like a chemistry kitchen.
Yep.
So what's our recipe for acid hydrolysis, Wayne?
Good question. Well, we
Right.
need a pinch of acid.
Right.
Yep. A dribble of heat.
I'm not doing that.
That's not good. We obviously need your ester, and you need a cup full of water.
That's lovely. So now I've got these things, it's quite toasty in there.
Yes, we've got to make sure that it's hot, acidic conditions.
Yeah.
That's why you need a dribble of heat.
Yeah.
So when we do that, we've got this over here. We've got this. I'm going to draw in red what we already have.
Okay.
C to a bond into O, to C to a bond into O, and it's going to break here and here.
It
Okay,
is.
so that's what's going to
It's going
happen.
to break it all into monomers, which is well good. Then our OH, as Wayne said, is going to attach here. I'll draw it in purple, the blue's running out.
So this OH is coming down here and down here. So we have a double-ended carboxylic acid thing.
Yeah, and that's pretty all fun and dandy. And then the other half
Yep.
forms our double-ended alcohol.
Yep, so we have this that we had before. The alcohol always takes the oxygen because when they get divorced it takes an oxygen.
Yeah, that's how that works. And then the H's from both sides, green, drawn blue, have appeared there. And that's our acid hydrolysis.
And that's lovely.
That is lovely.
That's just forcing water in and forming back the monomers that you started with.
Yeah. Now we're going to do alkaline hydrolysis, or basic hydrolysis.
Yep. So if I go down the middle here,
That's a good
might not even be
idea.
able to see that because it's green, but there's a line down the middle. These are two different routes.
Base. So, if you imagine what we have here is where the chemzo is, we still need to break.
Yeah, so we're breaking this exact same thing,
Yeah.
but we're not forcing water in now.
Well,
we could.
but we're not going to, for the sake of being different, we're going to add sodium hydroxide.
Yeah, that's a good example. Like we said, we could add water, but it would be difficult to explain what's different between the base and the acid if we
Yeah.
added water. Whereas this, you can clearly see a difference.
Yeah, so we have our thing. Now in our thing we have our carboxylic acid half.
So it looks like this, as it did here.
and our alcohol half.
And again, it looks exactly the same. It keeps them, and because it's getting divorced, it keeps the oxygens.
It does. Now, how does our NaOH split is basically the big problem.
It is indeed.
So what happens is it splits there.
It does, not the way you'd think. It doesn't split up into Na plus and OH minus.
No, it splits into our H plus, and that's what goes here.
Yep, because this still needs a hydrogen. This, to make this an alcohol, needs a hydrogen. Again, it's going to come over here, and it's going to do it twice. Because that makes this an alcohol.
It does.
That means what's left has to go over here.
It does. So the O will go here because it's carboxylic acid, it needs that.
Yep.
But then our Na is going to bond. How's it going to bond when?
Ionically, not covalently. So don't draw a line between the O and the Na. Even if you do put the charges, a line indicates a covalent bond, and you will be marked down.
So that's bad, don't do that.
Make sure you don't draw a line between them.
So the thing that we're doing differently here, well, it could be water, you won't be able to tell the difference would be, but funky stuff generally just goes to the carboxylic acid.
Yeah, it does, yeah. So if this was water, it would look exactly the same as this. It would be exactly the same.
So some things use ester, polyesters.
Yep. Other times you might use a polyamide instead of a polyamine.
Which is a bit different, so we'll go through that one as well. Essentially, it is the same before we've made them by taking water away in condensation. We're going to break them by putting water in hydrolysis.
But instead of an O here, we have an amide bond. This N to H go into the CH. And over here, instead of an O, again, it's going to be this N to an H.
Now, for both of these, it's important that they're both hot, alkaline and acidic.
Yep. So again, there's the two routes. I'm going to go from both again.
Yeah.
This has to be hot acidic conditions. So, what are we doing?
Well, similar thing before.
Exactly the same.
We're breaking the amide bond here.
Yep. So you can circle that, and we're forcing in water.
We are.
So it's the same as before, but it's going to be slightly different in a minute.
Yeah.
So we're still forcing water into this bond.
We are. So when we force that in, it will split.
Yep, it's going to split into OH and H again, and the OH is still going to go to the carboxylic acid,
So I'll start drawing those up.
and the H is going to go this way. And as for the carboxylic acid, altogether, it's actually exactly the same. We're still adding an OH, both here and down here on that side. So we get our double-ended carboxylic acid again.
We do. It's the amide half that's a bit weird.
It is. Because we do take an H, but this is in hot acidic conditions.
So
And
there's
in
H
hot
pluses
acidic conditions,
everywhere.
yeah, there's lots of them. And so we're going to add another hydrogen. It doesn't come from the water, it does come from the acid.
Yeah. So that goes in, and that makes it a bit different. It makes an unbalance of charge.
Yep, so we have this.
So you have an NH3, is what we had to start with.
Yep.
Adding more H's.
We're adding two H's either side, one from the
Yeah.
water, one from the acid.
So the water one, say in blue, and okay, both in the blue.
Oh, sorry.
That's fine. And then both of them will be charged.
Yep, so
Is it
indication of positive, if you put it in a circle you won't be penalised. Anything like that, as long as it's clear, it's slightly positive on both sides, because you're adding two hydrogens, one from water, one from acid.
That's your difference in the acidic side to go on to the base side. Again, choose NaOH.
Yep. So now you'll be able to see a difference with NaOH. So
So-
we're breaking up this one now.
Yeah.
So again, we're going to break up the same bond, and we're going to start with the same thing. It's going to have this, and something's going to happen to it. And we're going to have these two carbons with an N to an H on either side, and they're going to have the four hydrogens again unaffected. Don't need to draw them on.
But is it split the same way?
It is indeed going to split in the
Fantastic.
same way.
So this
Not
half,
the way you'd think.
we'll go over here.
Yep, so again, this side is unchanged. Just like in the acidic way, the result for the carboxylic acid side is unchanged. Again, don't draw a covalent bond, they're ionic. And then an H from here is going to bond to each of these, but because it's hot aqueous rather than hot acidic, there's no extra protons jamming about, so it forms
just that
NH2.
one.
There's no positive charge. The reason it's positive here is because there's three altogether. There's only two here.
Yeah, and that is the full story. So you want to save all the penguins. This is how you do it.
Yep. There's also something called photodegradable.
There is. So that's a bit different. The UV will affect one of the carbon double bonded to O bonds.
Yep. Or it might even affect all of them. And what it does is it vibrates, so it gives them energy, it makes them vibrate, eventually they'll break.
Yeah, and this will make, as it's the backbone of the entire polyester or polyamide, this will break up the entire thing anyway.
You don't have to know much of the details, you don't have to know like a mechanism or anything, but just appreciate that you can break these up by UV, so
Yeah.
sunlight, photodegradable.
That's good, that is.
That is good. So if turtles did swim in a bowl of hot, acidic conditions, and you dropped a biodegradable thing in there,
That'd be fine.
they'd love that.
Yeah.
So soup.
Yeah, I think that's a good idea. I love soup.
Now you might have noticed during this video we've held up a Morrison's bag,
A Poundland bag.
and in the corner we've drawn a little bag, and in the other corner we've drawn the very popular company Apple.
Yeah. Now, this is not to suggest that Clever America Squared has any affiliation between Morrison's, Poundland, or Lidl.
No, all supermarkets offer alternatives to these terrible, terrible, environmentally unfriendly bags.
And all of them are as good as each other.
Unless you sponsor us.
And then Aldi's great.
Yes, so that would be great because we're only really here for views and subscribers.
Yeah. So subscribe.
Please.
Yeah.